All right, good evening, ladies and gentlemen. It's time for the next lecture video. Today we're going to cover key features, okay? We're going to do graphing linear functions and key features. So the objective today is that we will identify and define key features for linear functions, because those are the first kind of functions we're going to look at in this class. The essential questions are, what are the key features of a function, and why are these important? Why do we look at these features? Because there's no reason to look at them, then why do I need to know how to find them? Okay? So, before we move on from this essential questions stuff, I've used key features like 4 times already, and we haven't even got to a lecture, and you probably don't know what I'm talking about. So key features are going to be things like domain, range, especially for linear functions, slope or rate of change. You also want to know things like the y-intercept and the x-intercept. Y'all have probably spent a lot of time so far in your math careers looking at this guy, the y-intercept, but not a whole lot of time looking at the x-intercept. So we're going to start looking at that because it is important for these relationships. Okay, and because we have already in this course covered domain, range, and slope, and I have videos on all of those things available on my YouTube channel, we're not going to define those. We already have a definition, a working definition for those terms. So, next thing we're going to do is definitions, and we're going to define y-intercept and x-intercept. Okay? Now, what you really want to know about these things and we're going to be pretty straightforward with our definitions. Okay, the y-intercept is going to be where this function or relationship touches the y-axis on the graph, or has an x value of 0. Okay? Now I understand that that can be a little confusing. We'll look more specifically at examples of this, but this one is a very important one to note. Okay? If you make your x value 0 in the equation or function, you automatically set the condition to get your y-intercept. Okay? Now, the x-intercept, you guessed it, is pretty much the same thing except all about the x-axis. So this is going to be where this function or relationship touches the x-axis, or where it has a y value of 0. Okay? Again, this one is important because just given an equation, you can force the equation to give you this. Okay? If you're given an equation that models the situation. All right? So now that we've taken definitions, if you need more time to write those down, go ahead and pause your video. We're going to move on to examples. Okay, so we're going to look at a few situations here, and I'm going to pull all of this information out of just these 3 situations. Okay, in this situation, you're told that Sarah has $300 in her bank account, and she spends $50 a day, we're assuming, until she runs out. Okay, so given just this relationship, not being able to write an equation or anything, I can certainly graph it. Okay, I can certainly graph that thing. So this is where you're going to learn or review how to graph situations. Okay, she says she's given, so she has $300 on day 0. That's the beginning point. Okay, where we start is with $300. So we're going to put that on our y-axis. Okay, there's your first point, the $300. All right. Now, she's spending Remember, she's spending $50 every day. Every day. So on day 1, we lose $50. So we went from 300 minus 50. That's going to give us 250. So there's the next point. Okay, day 2, now we have 250 and we lose another 50, so we're down to 200. Day 3, lose another 50, you're down to 150. Day 4, lose another 50, now we're down to $100. You can see this horrible trend coming out. Day 5, down to $50. And day 6, we have nothing left after day 6. Now this didn't quite come out like I wanted it to, like a straight line, but that's okay because y'all know that we're not losing different amounts of money every day. It's $50 every day. So we know that this should be a straight line. Okay, we should get a straight line relationship here. Okay, I just spaced these out too far. That's okay. So just imagine that this is a straight line angling downward. And given that information, now that we've graphed it, we can find a lot of the information we want. Okay, let's start with the review. Let's start about domain. Okay, if you remember, domain is all possible x values. Okay, so looking at this, our x-axis goes from 0 to 6. Okay, we start with $300 on day 0. And we end on day 6 with nothing left. Okay, but given this situation, you have to determine, is this continuous or discrete? Okay, am I spending 8 cents every minute each day? Okay, that adds up to $50. Probably not. I'm probably just dumping $50 at one place every day, which means that would make and this is a good time to amend and say continuous or discrete is another key feature. So that would make our argument that this is a discrete relationship, okay? And with that, it's all about how you argue it. Okay, so that would make my domain, all the x values, we can be day 0, we can be day 1, we can be day 2, we can be day 3, we can be day 4, we can be day 5, and we can be day 6. But we're not going to go past that because we're just talking about reasonable domain. And when we're being reasonable, we don't spend money we don't have. So we're not going to go negative here. We're just looking at quadrant 1. Okay, we're not going back in time, negative days. Okay, just from day 0 to day 6 incrementally. Now let's talk about the range. Okay. Our range here is going to be the same thing but for our y-axis. All the y values from up here all the way down. And we did say that it's discrete relationship, which means that we're not, again, spending 8 cents every minute, which means 4 cents every half a minute and all that stuff. We're just one day, $50. So given that argument, our range is going to start here, 300, and then we had 250, and then we had 200, and then we had 150, and then we had 100, and then we had 50, and then we had 0. Okay, then we had nothing left, and there's the range. All right. So we talked about domain, we talked about the range. Now we want to look at the rate of change or slope. Okay, so let's talk about the rate of change for this thing. If I want to write out the points for this problem, just the straight ordered pairs here. Pick this point, sure. X is 0, 300 is a y. All right, now take any other point. Sure, this next one. X is 1, then we have 250. Now, given that, I can find a range. We just have to put it in a table. 0, 300, and then 1, 250. Okay, this is x, y. All right, now we're looking at change from 0 to 1 for the x, you get positive 1. And from 300 to 250, starting here and going to 250, that's a change of negative 50. Okay, Rate of change is delta y, change in y, over delta x, change in x. So the y is right here. That's negative 50 over, the x is here, positive 1. So our slope, or our rate of change here, is going to be negative 50. Okay, because we're losing $50 per day. Okay, she spends $50 every day. So it's negative 50. All right, so we've done domain, range, rate of change. Now let's look at y-intercept. Okay, looking at the y-intercept here, I'm going to fold this down so we can have some space to work. Looking at this situation, here's your y-intercept. Okay, that's on the y-axis. But remember, the definition, if we go back to that, your definition is where the function or relationship touches the y-axis on the graph or has an x value of 0. Okay, in this graph, where is our x value 0? It's right here. Okay, so your y-intercept is 300. Okay, and it's also right here. Right here, your x value is 0. So that's going to make this number the y-intercept. Okay, so your y-intercept is 300. And you can put dollars, whatever you want. Okay, x-intercept. Remember, from the definition, the x-intercept is where this function touches the x-axis and or has a y value of 0. Where does that occur? Well, that occurs right here. Okay, that's where it touches the x-axis. That is literally the point 6, 0. See, the y value here is 0. So your x-intercept is going to be 6. Okay, when y is 0, I'm on the x-intercept, on the x-axis. And that is all of the key features for that situation. It's a lot of information, but being able to pick all this out gives us a lot of intuition, a lot of understanding of the situation. Okay, so let's go to the next example here. Okay, next example. Okay, this is going to be from a table. A table below shows the altitude of a plane when it leaves the runway. Okay, so we have a plane, its altitude, after 5 minutes it's at 6,000 feet, 10 minutes, 12,000 feet, 0 minutes, 0 feet, 50 minutes, 60,000 feet. Okay. So given this table, we want to find the range. Okay. Now, this is where it might be a little confusing because I really want a reasonable range. I don't want you to tell me that the y values can span from 0 to infinity. Is a plane really going to go infinity feet high? No, that's not possible. Planes are not made for space. So, we want to talk about, I'm probably going to use this one, right? That looks like a pretty good cruising altitude. And that's the highest value. So, not given a whole lot of information here, just understanding from the information of the problem, that's going to be my highest point. Okay, now where did the plane start? What's the lowest point? Is it going to start underground? Probably not. So we're going to pick 0 feet as my lowest point. So it goes from 0 feet to 60,000 feet. Now here's where the next piece comes in. If this plane just goes from here to here, then we have a discrete function. But do you think the plane's going to jump instantaneously from 0 to 6,000 or 6,000, 12,000? It's going to make that jump. It's not actually going to travel through the space. 6,001 foot, 6,002 foot, 6,003 feet. Right? It's probably going to travel through each one of those altitudes, no matter what time it is. So this really means we have a continuous situation. Okay, it goes through all of the feet. It goes through 6,001.2 feet, and all of that stuff. So this is continuous. Please excuse me while I try and spell continuous. Okay, that looks okay. So this means that my range is going to be inequality notation, with 0 being the smallest, y. Okay. Now let's look at the domain. It looks like we started at 0 minutes. Okay, we're not going to go back in time when it's taxing. That wouldn't make sense. Okay, so we're going to start this at 0 minutes, and we're going to end it with the highest altitude, 50 miles. Okay, so from 0 to 50 minutes. Sorry, 50 minutes. From 0 minutes to 50 minutes. So my domain is going to be 0 less than or equal to x less than or equal to 50. Okay. Now let's take a look at the slope here. Again, I wrote rate of change, I said slope. That means they're interchangeable. They mean the same thing, guys. Okay. Delta y over delta x. Well, let's do the work here. How did we change from here to here? We added 6,000 feet. How do we change from here to here? We added 5 minutes. Okay, which one's y? The feet, so that's going to go on top. 6,000 feet over 5 minutes. Now, if I was giving you a quiz or test, I would definitely expect you to reduce this fraction. Okay? Definitely expect that. I'm not going to do it because I don't have a calculator handy, and that's big numbers. It's okay to need calculators. That's fine. All right. Now we need to talk about x-intercept and y-intercept. Okay, and really to do this justice, we need to kind of sketch a graph. Okay, so I'm going to sketch a graph here. Looking at this situation, we can say that the graph is going to look something like this. The plane starts here at the origin, and it goes up and up and up. We're expecting at a steady rate until it gets to 50 minutes and a y of 60,000 feet, right? Okay, so there's our graph. This, of course, is the x, and here's your y-axis. Where does this thing touch the x-axis? Right here. Okay, that's your x-intercept, and it's the point 0, 0. That's the origin. Okay, so our x-intercept is 0. Now, where does it touch the y-axis? Right there at 0, 0. So our y-intercept is also 0. When you get situations like this, where you start at the origin, 0 time, 0 feet, your x and y-intercepts will be the same point, okay, 0, 0. That's okay. It just means that we have a really distinct starting point for this. Okay, not a problem. And there is all of the key features for that situation. All right, very last situation. I know y'all are tired of talking about this, okay, but here's the situation. Again, guys, I probably should have said this at the beginning, but you should probably be pausing the video and writing these situations down so you understand what's going on. That would be really good. Okay. So in this one, this is going to be from an equation. And we're looking at Mary. And Mary's, she's a pretty accomplished interior designer. And she makes $600 for every room she decorates. Okay? Every room she puts her stamp of approval on, she makes $600. She also makes a $100 fee just for accepting the job. You pay her $100 just to say, yeah, I'll do it. Okay? Her pay can be modeled by the equation y equals 600x plus 100. Okay, so there's the equation that we're going to use. This governs how much money she makes, where y is her total pay and x is the number of rooms she's decorated. And I'm going to add a little bit here. I'm going to say that she decorates at most 7 rooms. Okay. Okay, so last problem, here we go. Let's talk about the slope first, the rate of change. Okay, so we're going to talk about slope, or your rate of change. Now remember, this equation looks mighty familiar. It's just point-slope formula. I'm sorry, slope-intercept formula. Y equals 600 x plus 100. Okay, where this guy is your M and this guy is your B. Okay. So we have a slope, or M, of 600. Done. Given to us right in the equation. All right. Now let's talk about your y-intercept. Looking at the y-intercept, well, it's also right here, okay? B is the y-intercept. This is slope-intercept form, so your y-intercept is 100. We know that. Done. All right. Now, let's move on to the tough crackers, okay? The x-intercept. Now, in this problem, the x-intercept is not really going to be a practical point. So you could, if I said a reasonable x-intercept, write there is none. Because our x-intercept, if we look at the equation, here's the y-intercept. It's going to look like this. So our x-intercept is negative rooms. Are you ever going to ask somebody to decorate negative number of rooms in your house? No, that's never going to happen. So it's none. But if we were given just a pure equation, like the one you got in this problem, and said, find the x-intercept of this equation, then I would use the definition to find the x-intercept. And that definition is where it touches the x-axis, or where the y value is 0. Okay, so let's use the definition. If we make the y value 0, how many variables do we have in this problem? One, just x. And we can solve for that. So let's go ahead and do that. Okay, so I'm going to subtract 100 from both sides. Okay, then you get 100 equals 600x. Negative 100 equals 600. Then I'm going to divide both sides by 600. Remember, we're getting x by itself. So you have negative 1 over 6. I reduce this fraction all in the same step, okay? So I reduce the fraction. Negative 100 over 6 is the same as negative 1/6. And there's my x-intercept, okay? Negative 1/6 right there. Okay, so we forced y to be 0 because that's the definition of your x-intercept. And we solve the equation to get negative 1/6. If I have the point something comma 0 for this equation, that ordered pair, the something will be negative 1/6. That's the only way that this is satisfied. All right, so we've done slope, y-intercept. Now we have domain and range. Now, your range, let's start with domain. Okay, looking at the problem, domain is going to be the number of rooms. Okay, your x value is going to be, in this problem, total pay, and x is the number of rooms she has decorated. Okay, and domain is all your x's. So your domain is going to be the number of rooms. How many numbers of rooms can she decorate? Can she decorate 0? My argument is yes. Why? She can accept $100 to do the job, and then I can tell her, never mind, I don't want you to do this anymore. 3 minutes after she stepped into my door, I still owe her $100. So yes, 0 is on the plate. Okay. We can do 1, we can do 2 rooms, 3 rooms, all the way to how many will she accept? She decorates at most 7 rooms. 4, 5, 6, 7. Okay. Now, our range. If she decorates 0 rooms, how much money would we pay her? $100. She decorates 1, we pay her $700. She decorates 2, $1,300. 3, $1,900. 4, you see I'm just adding 600 every time. Okay, 4, $2,500. 5, $3,100. 6 would be $3,700. And 7 would be $4,300. Okay, and she decorates a maximum of 7 rooms. So that's the maximum amount of money she's ever going to earn on a single project. All right? So there is your domain and range. Now looking at this domain and range, would you say this is a discrete or a continuous example? I'm going to say discrete. Make sure you write that it is discrete down in your notes because that is also a key feature. All right, ladies and gentlemen, you have a fantastic night. Make sure you upload your notes to Canvas for grading, and I will see y'all tomorrow.